Good day everyone and welcome to our next lesson. In this video, we'll be talking about convective mass transport. Let's begin. Convective mass transfer has a lot of similar characteristics to convective heat transfer. In fact, there are some aspects that are completely analogous between convective mass transfer and convective heat transfer. One of the first similarities that you can see is that our main equation for the rate of heat transfer and the rate of mass transfer looks similar. As a review, our rate of heat transfer is equal to HA times delta T, wherein H is your heat transfer coefficient, A is the heat transfer area, and delta T is the driving force or the temperature difference. If you take a look at our rate of mass transfer, that is signified by small n sub A, that is equal to Kc times A times delta Ca. Kc is what we call the mass transfer coefficient. So the mass transfer coefficient works in the same way as the heat transfer coefficient. And then again, our A here is the mass transfer area. Delta Ca is the difference in concentration or the concentration gradient. If you go back to our discussion on convective heat transfer, the most important dimensionless number there is the Nusselt number, wherein the Nusselt number is a function of the Reynolds number and Prandtl number, and then the Nusselt number is equal to HL over K. Now, this is for forced convection because we are using Reynolds number instead of Rayleigh number. But regardless, Nusselt number is very important for convective heat transfer. The equivalent of Nusselt number in mass transfer is the Sherwood number or SH. The Sherwood number is also a function of the Reynolds and the Schmidt number. So we are introducing two new dimensionless numbers here. The Schmidt number is the equivalent of Prandtl number, and the Sherwood number is the equivalent of the Nusselt number. So let us define the Sherwood and the Schmidt numbers. The Sherwood number relates the surface concentration gradient to the overall gradient, just like the Nusselt number does in heat transfer. So we solve for the Sherwood number as Kc times L over dAB, wherein Kc is your mass transfer coefficient, L is the characteristic length of your system, and dAB is the mass diffusivity. We have already tackled this in our discussion in diffusion. Next, we have the Schmidt number or SC. The Schmidt number is the ratio of momentum diffusivity and mass diffusivity. If you compare this to the Prandtl number is the ratio of the momentum diffusivity and the thermal diffusivity. Okay? So Prandtl number is for heat transfer, Schmidt number is for mass transfer. Let's solve our first example. Determine the Schmidt number of methanol in air at 25 degrees Celsius and 1 atmosphere and methanol in water at 25 degrees Celsius. So we will be discussing a little bit of concept about this solving of the Schmidt number because this will involve us determining the diffusivity of methanol in air and methanol in water. For our first system, we are given methanol diffusing in air at 25 degrees Celsius and 1 atmosphere. So let's take a look at the formula for the Schmidt number. Schmidt number is equal to momentum diffusivity over mass diffusivity, and momentum diffusivity is viscosity over density. So we have the formula mu over rho times dAB. Therefore, we have to assess three physical parameters of the system: viscosity, density, and diffusivity. Let us start with the diffusivity dAB. So where do we find values of dAB? Well, if we take a look at our handbook, we have table 2-324 for the diffusivities of pairs of gases and vapors at 1 atmosphere. It is important to take note that our system is methanol vapor in air. So this is a gaseous system. So you simply have to look for the substance. Our substance in this case is methanol because that is the diffusing species. And then the substances here at the topmost row are the partner gases. So let's look for methanol. So methyl alcohol or methanol at 0 degrees Celsius when diffusing in air has a mass diffusivity of 0.132 square centimeter per second. But take note that this measurement was done at 0 degrees Celsius and at 1 atmosphere. Our actual temperature is 25 degrees Celsius and our pressure is 1 atmosphere, so we would need to adjust our value of diffusivity in terms of temperature. If you'll recall, our adjustment formula is D1P1 over T1 raised to 1.75 is equal to D2P2 over T2 raised to 1.75. Since pressure is the same, it's 1 atmosphere, our conversion equation will become D2 is equal to D1 multiplied by the ratio T2 over T1 raised to 1.75. Okay? The 0.132 square centimeter per second diffusivity was taken at 0 degrees Celsius. So let us solve for the diffusivity DAB at 25 degrees Celsius. That would be 0.132 divided by 100 squared to convert it to square meter per second, multiplied by the ratio 298.15 as our T2, and our reference temperature T1 is 273.15 Kelvin. And this ratio is raised to 1.75. Our new diffusivity is 1.539 times 10 raised to negative 5 square meters per second. Now that we have our diffusivity, we simply have to evaluate the density and viscosity. However, the question is, since we have two components, that is your methanol and air, which values of density and viscosity do we use? Do we use that for methanol or do we use that for air? Well, for mass transfer systems, the diffusing species normally is dilute or has a lower concentration than the partner species. So for the computation of the Schmidt number, you always take the physical properties of the solvents or of the compound that has the higher concentration. In this case, since methanol is the diffusing species, we then evaluate density and viscosity for air. Okay? Always remember that. For liquid systems, you evaluate the density and viscosity of the solvent. For the density of air, you simply have to use our ideal gas equation, Pm over RT, wherein the density is simply dependent on the pressure, molecular weight, and the temperature of the substance. Let's substitute. We have pressure, 1 atmosphere, 101,325 pascals, molecular weight in kilograms per mole, that is 0.029, divided by R, 8.314, and then our absolute temperature, that is 25 degrees Celsius or 298.15 Kelvin. Our density is now 1.185 kilograms per cubic meter. Now for the viscosity of air, you need to evaluate that using our table in the handbook. I have calculated that to be 1.85 times 10 raised to negative 5 Pascal seconds. Now that we have the diffusivity, density, and viscosity, we can now substitute everything to the definition of the Schmidt number. That is 1.85 times 10 raised to negative 5 divided by 1.539 times 10 raised to negative 5. That is our diffusivity multiplied by the density 1.185. Our Schmidt number is 1.01. Okay? Always remember how to adjust the value of the diffusivity with varying temperatures and pressure. Also remember the definition of the Schmidt number, and always remember which component do we determine the properties density and viscosity. Let's now have the second part of this problem. For the Schmidt number of methanol in water at 25 degrees Celsius, we are still working with the same equation, that is Schmidt number is equal to mu over rho dAB. The only difference is that we are now evaluating the diffusivity for pairs of liquids, that is methanol and water. For that, we are going to use a different table from our handbook, that is table 2-325. We have the diffusivities in liquids at 25 degrees Celsius. So it just so happened that our given is already 25 degrees Celsius. But I will be teaching you how do we adjust the value of the diffusivity if you have a different temperature. So let's look for methanol under the solutes, and solvent is water. Here we have methanol, solvent is water. The diffusivity is 1.6 times 10 raised to negative 5 square centimeter per second. Now this value of the diffusivity already is at 25 degrees Celsius. But if you need to adjust the value of the diffusivity, for pairs of liquids, we have the formula D1 mu1 over T1 is equal to D2 mu2 over T2. This conversion formula is different from the one that we use for pairs of gases, okay? So please do take note of the differences. For this conversion equation, you have to evaluate two viscosities, one at the reference temperature, that is 25 degrees Celsius, and the other at your actual system temperature. Well, in this case, since we have the same system temperature as our reference temperature, we don't need to adjust anything. We just have to convert the value of our diffusivity from square centimeters per second to square meters per second. Next part, we also have to evaluate the density and viscosity for the system. Now, in this case, since methanol is your solute and water is your solvent, you have to evaluate the density and viscosity of water at 25 degrees Celsius. So you can do that with our previous tables. For the density of water, that is 996.96 kilograms per cubic meter, while for the viscosity, that is 9.13 times 10 raised to negative 4. So we can now solve for the Schmidt number, that is viscosity, 9.13 times 10 raised to negative 4, divided by diffusivity, 1.6 times 10 raised to negative 5. We divide this by 100 squared to convert it to square meters per second, and then we multiply the denominator by the density, 996.96. Our Schmidt number for the liquid system, 572. In here, you see a big difference in the values of the Schmidt number for the gaseous system and for the liquid system. Okay? And that is how you evaluate the Schmidt number. Let's go back. Now that we know how to determine the Schmidt number, let's now go to the determination of the mass transfer coefficient, Kc. We will first be discussing the theoretical models, and then later we'll be discussing the empirical models used to determine Kc. The Reynolds analogy applies if both the Prandtl number and Schmidt number are equal to 1. If you'll remember, back in our discussion of forced heat convection, we can use the Reynolds analogy if the Prandtl number is equal to 1. Well, if both the Prandtl and the Schmidt number are equal to 1, we can extend the Reynolds analogy not only to heat transfer but also to mass transfer. So we have our analogy here, Stanton number is equal to F over 2, F is the fanning friction factor, that is equal to H over U rho Cp. This is simply the definition of the Stanton number. While for the mass transfer side, that is equal to Kc over U, or the mass transfer coefficient over the velocity. Okay, so the F over 2 is from momentum transfer. H over U rho Cp comes from heat transfer. And from mass transfer, we have Kc over U. We have now completed the Reynolds analogy. By the same token, we have the Chilton-Colburn analogy. The Chilton-Colburn analogy applies if the Prandtl and Schmidt number are no longer equal to 1. So for the momentum transfer side of Chilton-Colburn analogy, we have F over 2, same as the Reynolds analogy. For the heat transfer side, we have Stanton number multiplied by Prandtl number raised to 2/3. But take note that the Stanton number here refers to the heat transfer coefficient because we also have the Stanton number for mass transfer. On the mass transfer side, we have the Stanton number for mass transfer multiplied by Schmidt number raised to 2/3. We can also extend both the Prandtl and the von Karman analogies for mass transfer, but they are only applicable for turbulent flow. So we have here our Prandtl analogy. We have Sherwood number is equal to the following. And then finally, the von Karman analogy, Sherwood number is equal to the following. If you notice, we only changed the Prandtl number to the Schmidt number. Okay? So these are analogies between momentum, heat, and mass transfer. Now, if you don't like using analogies, we can always use empirical equations. Other empirical equations for Kc can be found in our handbook. Care must be exercised to correctly select the appropriate model regarding shape. That could be a disc, cylinder, sphere, plate, or other miscellaneous shapes, phases, solid, liquid, or gas, flow regimes, laminar or turbulence, and other conditions. So let's go through the table to show you how many correlations do we have for Kc. As you can see here, we can use table 5-17 along with the other tables to find for our mass transfer correlation. So let's take a look at some of these equations. So if we have laminar flow along a flat plate, and that is forced flow, meaning that is forced convection, we can use this correlation. Sherwood number is equal to mass transfer coefficient K multiplied by X, or the length of the plate, divided by D, or the diffusivity. That is equal to 0.323 times Reynolds number raised to 1/2 times Schmidt number raised to 1/3. We have here on the third column some comments, and you can read those comments to see if that equation is applicable to your system or not. We have many equations here. Table 5-17 is for single flat plate or disc, wherein the transfer of mass is to or from the plates to the fluid. We also have mass transfer correlations for falling films with the free surface in wetted columns, so you can have those equations. Mass transfer correlations for flow in pipes and ducts. So if your fluid is flowing inside of a pipe and then there is mass transfer happening, you may use these correlations. The most important thing to note here is you need to know if the flow is laminar or turbulence, and we can do that with the use of the Reynolds number and then select our appropriate equation. You might also notice here in the comments that there are ranges for the Schmidt number as well. So you have to evaluate your Schmidt number and then take a look at the comments to see if your system falls within that range of the Schmidt number. We also have mass transfer correlations for flow past submerged objects. So this is for external flow, for single spheres, for single cylinders, and so on and so forth. Okay? So you have to take a look at these tables for you to be familiarized with the equations. Let's try to solve this example. Air passes through a naphthalene tube that has an inside diameter of 2.5 centimeters, flowing at 15 meters per second. The air is at 283 Kelvin in atmospheric pressure. Assuming that the change in pressure of the air inside the tube is negligible, and that the naphthalene surface is at 283 Kelvin, determine the length of tube that is necessary to produce a naphthalene concentration in the exiting gas stream of 4.75 times 10 raised to negative 4 moles per cubic meter. At 283 Kelvin, naphthalene has a vapor pressure of 3 pascals and a diffusivity in air of 5.4 times 10 raised to negative 6 square meters per second. Here are our given for the problem. So we have a tube 2.5 centimeters in diameter with air flowing inside at 15 meters per second. So the tube is made of naphthalene, okay? And then the idea is that naphthalene will sublime into the air such that our exiting air would somehow contain some naphthalene. So we are looking for the length of the tube that is needed in order for our exit air to have a naphthalene concentration of 4.75 times 10 raised to negative 4 moles per cubic meter. So this is definitely a convective mass transfer problem because we are given a velocity of the air, and the air serves as the solvent that carries or dissolves our naphthalene. We will be approaching this problem just like how we are approaching forced heat convection problems. So if you'll remember, for forced heat convection problems, we simply have to determine the Reynolds number and the Prandtl number, solve for the Nusselt number, from there solve for the heat transfer coefficients, and then solve for the total rate of heat transfer. Okay? While for convective mass transfer, we simply have to solve for the Reynolds number, the Schmidt number, and then solve for the Sherwood number using our correlations, and then from the Sherwood number, determine the mass transfer coefficients, and then determine the length of the tube from there. So let's first solve for the Reynolds number. The Reynolds number is still du rho over mu, and since this is flow inside of a pipe, we determine if it's laminar or turbulence by the cutoff Reynolds number 2100. And for that, we first have to determine the density and viscosity of air. Remember that air is our carrying fluid here. That's why our properties are evaluated for air and not for naphthalene. Okay? So the density of air, that is Pm over RT. Our pressure is 101,325 pascals, molecular weight 0.029, and then R 8.314, and then temperature 283 Kelvin. Our density is 1.249 kilograms per cubic meter. Next, for the viscosity, evaluate this using our tables in the handbook. This is 1.77 times 10 raised to negative 5 Pascal seconds. This is at 283 Kelvin. Now we can solve for the Reynolds number. Our diameter, 2.5 centimeters, that is 0.025 meters, times the velocity of 15 meters per second, times the density of 1.249 kilograms per cubic meter, divided by the viscosity of 1.77 times 10 raised to negative 5. Our Reynolds number is 26,462. This is definitely turbulent flow. Next, we determine the Schmidt number. Again, Schmidt number is mu over rho dAB. We are just going to reuse the values of the viscosity and density of air, which we have determined earlier. And then the dAB, or the diffusivity, was already given. That is 5.4 times 10 raised to negative 6 square meters per second. Calculating the Schmidt number, that is 1.77 times 10 raised to negative 5 divided by density 1.249 multiplied by the diffusivity 5.4 times 10 raised to negative 6. Our Schmidt number is 2.62. Now we can determine the Sherwood number, but before that, we first have to decide which correlation do we use in this system. Now remember our system, we have a tube or we have a pipe wherein the fluid is flowing inside of the pipe, And then the transfer of mass occurs from the surface of the pipe to the bulk of the fluid. Okay, so let's look for our correlations. We need to determine the mass transfer correlations for flow inside pipe. Let's start here from table 5-19. First, let us look for the situation. We want our correlation to handle turbulent flow. Okay, so we will not be using A because this is just for laminar flow. For B, there was nothing indicated, so let's keep looking. These are all for laminar flow. So let's look for turbulent flow. Starting from letter Q, we now have turbulent flow. If you take a look at the range of the Reynolds number, this equation is only applicable if your Reynolds number is between 2,100 and 35,000. Our Reynolds number is 26,000, so we are well within range. Our Schmidt number is 2.62, so again, we are well within range. If you take a look at the comments, use with log mean concentration difference at two ends of the tube. And this is a good fit for liquids. If you take a look at this second equation here, this is a better fit for gases. However, the problem here is if you take a look at the Schmidt number, we have overshot it because our Schmidt number is 2.62 and the range says that your Schmidt number can only be up to 2.5. Okay, so with this, we can actually use the first equation even though it says that it's a good fit for liquids. It just says it's a good fit. It does not mention that it is prohibited from being used in gases. Okay? So let us use the first equation here. That is, Sherwood number is equal to 0.023 Reynolds number raised to 0.83 times the Schmidt number raised to 1/3. And then the Sherwood number is defined here as mass transfer coefficient Kc times the diameter of the tube divided by the diffusivity DAB. Do not confuse yourselves with the small d and capital D. In this case, the small d is for the diameter of the tube, and then the capital D is for the diffusivity. Going back, since we now have our correlation, we can now substitute our Reynolds and Schmidt number to determine our Sherwood number. Let's calculate. That is 0.023 multiplied by Reynolds number, 26,462 raised to 0.83 multiplied by the Schmidt number, 2.62 raised to 1/3. Our Sherwood number is 148.57. And this is equal to Kc times the tube diameter over the diffusivity DAB. From here, we can determine the mass transfer coefficient Kc. So we simply multiply the Sherwood number with the diffusivity, that is 5.4 times 10 raised to negative 6 square meters per second, and then divide that by the diameter of the tube. The diameter of the tube is 2.5 centimeters or 0.025 meters. Our mass transfer coefficient is equal to 0.03209. Now the question is, what are the units of the mass transfer coefficient Kc? If you take a look at our Sherwood number, the Sherwood number is a dimensionless number, meaning that the collection of units for Kc times diameter over DAB should all cancel out. Okay? And from there, we can determine the units of Kc. It should follow that the units of Kc would be equal to the units of DAB over diameter. So DAB is square meter per second, and then diameter is meters. If you take a look at the cancellation, one of the meters would cancel, and you will be left with meters per second, or it's the same unit as velocity. So the mass transfer coefficient actually has units of velocity. However, this is just a simplification. Since we are dealing with concentrations with units of moles per cubic meter, we would expect that the mass transfer coefficient would have a unit of meters per second. But in our next lesson, that is interface mass transfer, you will be encountering a different type of mass transfer coefficient with a different set of units. Okay? So the set of units of the mass transfer coefficient Kc would simply depend on the units of the concentrations that's being used. So it's different if the concentration is in molar concentration, that is moles per cubic meter. It's also different if the concentration is in terms of pressure. Okay? So for now, let us use this Kc with units of meters per second. Let's now identify our rate of mass transfer. If you will recall, we can write the rate of mass transfer due to convection as N sub A is equal to Kc, or the mass transfer coefficient, times A, or the transfer area, multiplied by the driving force delta Ca, or the concentration driving force. Okay? Now, where is the length of the tube going to factor in this equation? That is going to factor in our area. Because remember, A here is the area of transfer. That is the inner surface area of the tube. And that surface area is pi dl. Okay? So our equation is rate of transfer is equal to 2 pi dl times kc times delta Ca. We know the diameter, we know the mass transfer coefficients, and we also know the driving force. We simply have to determine the rate of transfer, and then we can solve for the length. So let me first tidy some of these things, and then we will proceed with the determination of the rate of transfer. Let's start by determining the volumetric flow rate of the air coming in and then coming out of the system. Since we have assumed that the pressure drop within the pipe is negligible, therefore we can assume that the volumetric flow rate is constant from the inlet to the outlet. Okay? We have to keep that in mind because our system, which is air, is compressible and it can have varying values of the volumetric flow rate if there is a change in pressure. Okay? Solving for Q, that is velocity multiplied by the cross-sectional area of the pipe. Do not confuse yourselves with the cross-sectional area of the pipe and the internal surface area of the pipe. They are used for different purposes. Okay? Expanding, this is velocity multiplied by pi over 4 times d squared. Substituting, that is 15 multiplied by pi over 4 times the diameter 0.025 meters squared. Our volumetric flow rate is 7.36 times 10 raised to negative 3 cubic meter per second. Now, this is the volumetric flow rate of air alone that is going through the system. Now, we know that air is not being consumed. So, therefore, we know that the amount of air is constant from the entry to the exit of the pipe. What is being added is actually the naphthalene. If you take a look at our concentrations, at the entrance of the pipe, we are assuming that there is no naphthalene. Let's say, for example, that it's just pure air or clean air. And then at the exit of the tube, we now have a concentration of 4.75 times 10 raised to negative 4 moles per cubic meter. If I multiply the exit concentration of naphthalene to the volumetric flow rate of our air, what we can actually determine is the amount of naphthalene in moles that is coming out of the tube per second. Okay? If we multiply cubic meters per second with mole per cubic meters, we get mole per second. And that is actually the rate of naphthalene that is going out of the tube. And since there is no naphthalene coming in of the system, whatever's coming out of the tube must be the rate of the sublimation of naphthalene, which is what we are after. Okay? So we write N sub A, or the rate of sublimation of naphthalene, is equal to the volumetric flow rate of air multiplied by the exit concentration Ca2. Let's multiply. That's 7.63 times 10 raised to negative 3 cubic meters per second multiplied by 4.75 times 10 raised to negative 4 moles per second. Our rate is 3.497 times 10 raised to negative 6 moles per second. This is for naphthalene. Okay? And then if you go back to our previously derived equation for the rate of mass transfer, that is N sub A is equal to pi dl times Kc times delta Ca. Do not be confused of the delta Ca here. The delta Ca is not exit minus entry. Or we can also say that delta Ca is not equal to Ca2 minus Ca1. Okay? Delta Ca here pertains to a driving force. And the driving force is the concentration difference. With that, let us define our delta Ca as concentration of naphthalene at the surface of the pipe minus the concentration of naphthalene bulk. The bulk concentration of naphthalene is simply the average of the concentration at the inlet and at the outlet. Okay, solving for Ca bulk, that is simply 0 plus 4.75 times 10 raised to negative 4 over 2. That is 2.375 times 10 raised to negative 4 mole per cubic meter. How about for the concentration of A at the surface? Well, this is a vapor system, so the concentration is simply P over RT, wherein P is the partial pressure of naphthalene at the surface. Now, we will be assuming that the partial pressure of naphthalene at the surface is equal to the vapor pressure of naphthalene. The problem has already stated that the vapor pressure of naphthalene at the stated 283 Kelvin temperature is 3 pascals. Substituting, our partial pressure and vapor pressure is 3 pascals divided by 8.314 times the temperature 283 Kelvin. Our surface concentration is 1.275 times 10 raised to negative 3 mole per cubic meters. If you compare the values of the surface concentration and the bulk concentration, the surface concentration is higher than the bulk concentration, meaning that the mass transfer will happen from the surface to the bulk of the fluid. Okay, so our driving force surface minus bulk makes sense. From here, we can now solve for the length of the pipe by dividing 3.497 times 10 raised to negative 6 moles per second, which is our rate of sublimation, with all of the other parameters except length on the right-hand side of the equation. So let's calculate. That is 3.497 times 10 raised to negative 6 divided by pi times diameter 0.025 times Kc, which we have determined earlier as 0.03209 meters per second, times the concentration gradient, surface temperature 1.275 times 10 raised to negative 3 minus the bulk concentration 2.375 times 10 raised to negative 4. The length of our pipe is 1.34 meters. Our interpretation is, if the length of your naphthalene tube is 1.34 meters, then if you have fresh air flowing at 15 meters per second inside of the pipe, as soon as it exits, the concentration of naphthalene will be 4.75 times 10 raised to negative 4 moles per cubic meter. Okay? These calculations for the convective mass transfer coefficient as well as the rate of mass transfer is very important in some applications in real-life systems such as humidification, air conditioning, drug delivery, controlled release of substances, and so on and so forth. So basically, if you will be increasing the velocity of flow of the fluid, then the mass transfer would happen faster. In this lesson, we have covered convective mass transfer from the same phases. So in this example, our naphthalene is already in the vapor phase before it transfers to the air. Okay, so there is no change in phase. On our next lesson, we will be dealing with mass transfer in different phases. So that could be from liquid to gas or from gas to liquid. Okay, please do watch out for our next lesson. That's it for this video. I hope you have learned something. Just keep in mind that convective mass transfer functions in the same way as convective heat transfer. Okay? Thank you for listening, and as always, keep safe.